Let's start. Welcome everybody. Good morning, good afternoon. Hope everyone is doing well. Welcome to this seminar from the Environmental and Social Responsibility Society for the Canadian Institute of Mining. Today we have the presentation of sustainable remediation in extreme mine wastewater ecosystem, and is going to be presented by Dr. Mark. So I will introduce her. She will present around 30-40 minutes of this webinar, and then we're going to have a Q&A session. Those who want during the presentation to send some questions, you can use the chat box as well, or at the end we can open as well the microphone and we can discuss on the different topics that we're going to present today. So let me first please introduce Dr. Margaret Cullen. She is a founder of the Bourgeon Research. It's a firm which has developed ecological based and self-sustaining decommissioning systems for mine waste and water management areas. She received the Noranda Award for Outstanding Achievement in Reclamation, as well as the Tech Cominco Environmental Award. In the year 2006, she was a nominated Distinguished Lecturer by the Canadian Institute of Mining. She's a retired qualified environmental professional and a senior ecologist of the Ecological Society of America. She held adjunct professorships at several Canadian universities. She has published more than 100 papers and contributed to chapters to many books. Bourgeon's report on the company's mine sites are available in the Laurential website. We will share that at the end of the presentation as well, so you can access with that information. And in 2022, Dr. Margaret, she published a book related to the extreme ecosystems of mine waste and water management areas. We will share as well in the chat the links for those books if somebody is as well is interested on this information. Margaret, I pass now to you. And again, we're going to have around 30-40 minutes on the presentation, and then we are going to have the Q&A session. Please, Margaret, go ahead.
Thank you for your introduction, and don't get scared. These honors which I received were definitely over a long period of time, and as you will see on the first slide, I changed that from the extreme environment. I think pile of waste rock, you can see if you look at it from an ecological point of view, it is an extreme environment, but this highly motivated person which speaks to you has not corrected mining wastes, but mining wastes. So please forgive me, I'm getting old. I noticed it and then I didn't change it. I started out accidentally, more or less due to my ex-husband in mining, because I visited Sheffield, this big hole in iron mining, and I thought one should do something about it. So now you have concentrated on the most promising remediation work, and that is the hindrance of the weathering process. So it's 40 years, and I have been working on tailings and waste rocks, piles, etc. And I never realized it, because as you get older, you get wiser, that I had the pleasure, quote unquote, to actually work on tailing sites and on waste rock piles. So I will focus on, in this presentation, mainly on the most important process, which I think I have done the groundwork in science. Therefore, and I think you will know, most of you are likely engineers. Engineers want to control nature, and science is trying to understand nature. So we go to the next slide, which I do now. And here you see why I think there are relevances in Yellowstone National Park. The blue is highly massive sulfuric acid, and the other picture is the steam. And if you put in Google and you put steaming coal mines or steaming mines, you will find the same thing. They catch fire. And lots of the natural processes, of course, take place. And what have we done when we produce a waste rock pile or a tailings pond? This is the waste rock pile. It's a schematic, and I never understood. I was working in the mining with the mining people, always with the decommissioning plans and with plans how to set the mine site up. And what I did never understand, okay, you have millions of tons in your waste rock pile, but they put lime according to the sulfate content, because that's the culprit who produces the drainage. However, within the waste rock pile, and you can go to every waste rock pile in this world, you have only pathways which end up with the seepage, but within here, weathering and oxidation, leachates mixing. So precipitates, secondary minerals are forming. It's a resolubilization process. And I had one waste rock pile, which I investigated for seepages. And the seepages in the north side of the pile, well, it wasn't a pile, it was like a wall, huge, up in Chemical, and the south side had much more seepages. Well, logically, because the temperatures are different in the high north. So what I didn't understand, that didn't make any sense, because what is the end result here is not what you get. And now you put equal amount of neutralizing, but the water doesn't get everywhere. So, one of the questions which no engineer explained me ever. Now, the drainages are sown in the industry sites, and we agree fully with that statement. But you can imagine, I visited a lot of conferences, and then some of these conferences have a panel at the end of it, and there is mining executives sitting there, and they do say things like, mining, we need metals, I agree, but I don't agree that it is the price to pay for metals. And, in one conference, I actually got up after one of the executives stated precisely that we can't do anything about it. We spend lots of money now on this. However, I got up and I said, gentlemen, if you state this and you believe it, I believe you had no other intent with this. There's a whole audience of 450 people and lots of young people, and we do want to solve that problem. And the whole audience was clapping. So I'm repeating that. What you hear now is what I think we have. Let's start thinking together. Are we actually looking at the right place when we look at the drainage? So you can do this yourself, but this is, one of my ways of explaining it. These are the number of references quoted, searched by Google Scholar, and this is the research intensity. It's the whole graph is called research intensity. And the interesting thing, I have made this red, and look at that. Everyone looks at water treatment. Well, water treatment is after the fact. The source, we have to do the work. Mine waste, okay, have a bit more, but I don't think it's the right place. If the microbes are indeed the major culprits, and you will find out a little bit more in other slides. So the mineral surfaces, what we have done when we produce a waste rock pile or a tailings, we have increased the surfaces which are available to weather, and hence, when we finally have a seepage, we have much, much higher concentrations of metals. So, the other thing is that we do therefore have to understand how are the weathering processes and how can we slow them? And that's what I hope to show you today. Okay, what else is very similar and where is lots of money spent? Weathering, erosion, and corrosion. And on corrosion, that is expensive, and a lot of people do lots of good research there. So it is, it's more or less a well-known process that first we have chemical weathering, then the microbes say, hey, this is a great place to live, and then the basic understanding in the literature is, the microbes increase the, the amount of weathering which takes place. However, when you go into the corrosion science, it's microbially induced corrosion, and there is a lot of good science which we can use and apply to the microbial increases. Well, I wanted to know, often in publications, it was stated that it is about 1,000 times a rate increase in weathering when the microbes are there. Well, by the time I found the actual quote, it is 1,000,000 times. That's why I have it stated in red. And 1,000,000 times, I think that screams for we have to get at these microbes. Now, in the industry, I think I have to state that I had a lot of support, really super support. Hence, I managed to actually work on these waste places and have nice pieces of paper. Watch out, the bugenites are going to be below the waste rock with an active waste rock, so we don't dump any waste on them, which were good things. You may laugh. I'm hoping you hear that and find it funny. I have it framed. The side of the problem, I think I have stated. Now, basically, I was considered a bit of a nutcase, thinking that one could stop the acid mine drainage. So what happened is that I heard, a mine manager of a uranium mine came up with the CIM magazine and said, oh, Margaret, it's probably your bugs. And what you see here is a rock from BC mine, and it was just a heap leach, and it didn't produce any more copper. So, I was known at the conferences, oh, Margaret wants all this money, okay, maybe we give her some. But in this case, I wanted the rocks. So, I did get a whole bunch of rocks. And this is how they looked like from the area which was no more producing copper. So, this we put under a microscope, and later you will see some pictures. And what did we find? Microbes. Now that was a real progress for us. And you can see on the next slide, that gave me the incentive to get, these are garbage cans. And we had a facility because Shell, Machapi, Billiton, they supported Bujum research for a while. And we started with 3 tons of waste rock from the Salbay mine in northern Quebec. And here you see the results. The pH, this one, the blue one is the control. And then we distributed a phosphate mine and a phosphate waste based on a field work by the West Virginia Task Force. They were in coal. So, they had, this was way back. But of course, I went to the place where that supposedly West Virginia Task Force had outdoor piles with different concentrations of phosphate mining waste, because there was an era that Dr. Evangelou was having master students doing on coal work, and he used phosphate because the people felt, and that is correct, if you add phosphate to high iron solutions, you get iron phosphate formed. But one of the rules of an ecologist, where there is phosphate, there will be microbes because they love to eat phosphate. So, I looked at the research very detailed, and after they, we were supposed to go to the piles, but we never did get there because the liming industry didn't like that whole thing. So I went to the conference and had all the details from the paper. I noticed, together with some people which worked with me, so, hey, the one with the least acid generated, virtually alkalinity generated, there has to be something which isn't right. So my company at one point at the Shell time, I had a microbiologist, an ecological microbiologist, and he looked at these curves from the West Virginia Task Force. And lo and behold, he said, you know what, the timing, they had also dates, when they started and so on. The timing looks just like a microbe formula. Okay, super. Now, that was the beginning. Now you can see here, mixed and layered. The pH was, it ran for 1,095 times, and that was high pyrite. That was weathered, that's already weathered, so there is already acid there. So we go to the next slide. we were certain it was microbes. So now we have to understand how microbes work. They most of the time work in forming, covering up the surface, the mineral surface. Then they, they propagate, and they have even signaling versions, not versions, substrates, which they tell, hey, we are too big, go and fly and become little floats and try to find a new place to settle. Microbes also accept electrons from their base, and the kinetic pathway you can see here. The biofilms are also when you get your water heater cleaned from time to time, and when you take a microscope, you see something like this. This was the SEM picture. Are you seeing my pointer? Hello?
No,
No.
try, it's perhaps in the other screen on your computer.
Here you see the pointer, right? Going from this big green stuff.
No, yet.
Oh, okay, that's a pity. But anyways, you see there are little tails on there, right?
Right.
Okay. Now these things here, you see the arrows, and below the arrows there are those round little sausages. This was on the fossil on the British Columbia Gibraltar leach pile, and this was after we were investigating. We got some money from the University of Toronto, and we had stored our experimental experimental drums for a long time, up to 11 years, and then there was a time it had to go. So one of these things which is important, you have to indicate that these things are not going away very quickly. So here you have a Nature review of microbiology, and the oldest biofilm dates about 3.25 million ago. So I think it's a one-way application. And every time I've had a new result, I figured, oh, wouldn't it be nice if the mining industry should get excited? No. Every single time, oh yeah, but which microbes are on there? And blah, 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 blah. There are no microbes on there. Yes, there are microbes on there, but I don't have the names. Now, you please note, so I gave some money to a postdoc at Essen, the University of Duisburg-Essen, the Biofilm Central. These people deal with nothing. So this first, the pH 1.5 is B1 and B3. You see there is electrical conductivity relatively high, and the volts measured, they have instruments to do that. Now B2 and B1 with this so-called NPR, natural phosphate rock, and they, by the way, the Virginia people were using ore. I used wastes, because if it would be ore, it would be too expensive. It has to be wastes. So the wastes worked fine, but it had nothing to do with the phosphate. This is the Springer book. Note how clear the water is. Unfortunately, the postdoc put a red box behind it, but this is just as B2 and B4 are just as clean. So now I have, the steriles, acidophilic heterotrophs, etc. And again, no big breakthrough other than in science. So now I get to the practical part. this was just one process, summary of ecological versus conventional costs. I don't know if anyone in the audience knows who Michael P. Sudbury is or was. He is now in the old age home. He has every award the CIM can give, and he was very supportive. He came, these are real figures based on the site where I had the biggest support. And, these are dollars, Canadian dollars. They are a bit outdated Canadian, no, it's US dollars. But I think he made that, anyways. Point is, you can see the ecological thing is much, much cheaper. So orders of magnitude. So that site is 45% pyrite and 5% pyrrhotite. I have made the application of impermeable cover over the tailings and other carbonaceous fine grit. We did them the science. What is it? It's carbonaceous material stimulates the biofilm to make a cover over it. Drilling and operations to well contaminated versus effluent intercept and high density lime sludge. Man, that mouse is a bit sensitive, excuse me, next. Okay, there is more to this, but not in the direction of inhibition, but treating drainage. Because until we can shut down a treatment plant, it will take a couple of years because, we also need, so for example here, this is a lake with pH 3.5 and the outcome is around 4. That's the end of, that's ARUM, acid reduction, that's in Selco, a coal mine. This is the seepage coming in here and all the iron precipitates. These are these carbonaceous coarse gravel sand. Then this is algae, and there would then be floating algae producing and reducing environment for the precipitation. That was the very first, and we are nearly at the end of the slides. I think with the time we are okay. Okay, nobody believed me with my microbes. And so I decided, okay, that is the very first site under the RACS program. That was the reactive acid program. And this was a site which was covered with pyrrhotite. The problem why I got the site to show my processes was no equipment could get on there. They all got stuck, so they couldn't seed it, etc. So this was a creek sorry. Okay, here you see it. This is a creek, very slow flowing. So what we did, we sectioned it up. And 1 year later, ferric iron was reduced to ferrous iron and all precipitated. So the pH values got up and the redox got down. And the story was rather nice. I wanted that the microbiologist, which I had hired for the company, that he came with us to actually, look at the site where it comes from. So we drilled a hole, it was all underneath ice, and a massive, stinking H2 hydrogen sulfide came out underneath, and and the pH values were up, and this is all encrusted. And to give it my effort a little bit of a management hint. The economic, this is a three-legged idea, economics, profit, My stuff is really quite cheap. And, you know, I have this technology review, that's the MIT technology review, already in 1990. Keith de Bas, who was a prof close to, what is this big open pit gold in California? No, not California. Forget it. It's big open pit. And he said mining with microbes, and he had entirely understood that the ecology approach works. And with this, I think I am finished. Yeah, these are just blank slides. So, any questions?
Thank you, Margaret. I think it was very interesting, all the presentation and all the development that you was working in all these years. And I was sharing as well on the chat the link for the book and the other link as well for the mining ecological engineering and metal extractions. And I was wondering, thinking on the microbial ecosystem reproduction, and I understand that these ones requires to have a liquid environment. And I was wondering if, with the new technology that are under development, looking for dry tailings, if you have a dry tailing area, if we compare with the tailings with more water presence, will be that cause a difference on the use of the microbes and the research that you was involved?
What I didn't entirely understand.
I mean,
the difference between the ecological approach.
Yeah, I mean the dry tailings, and we have the dry tailings, and we have.
You mean the Kid Creek?
Yes,
Right.
it will affect the process for the microbes to the reproduction and the process that they can use for with the metals, or there's any differentiation or things that your research you applied before?
Well, you know, I've worked in Kid Creek. It's a good concept, but at the bottom, you see, you always have a surface, right? And so at the bottom you have drainage, and that could be very easily dealt with ARUM, acid reduction using microbiology. Fundamentally, it's very important. You know, there is this big effort in terms of analyzing the ecosystem microbes with the supercluster work. The tailings, if one, you know, I would have a slide, but I don't know where it's gone. But, you know, the tailings are so heterogeneous. Number one, some of the tailings are with, you know, with just trees not cut. Anything organic around, that's where microbes have a great time. So, you know, I don't know if I answered the question correctly, but it's definitely applicable without any microbes to be added. You just need to change the environment in which the acid generating microbes are. They live in a biofilm, which is a single layer biofilm. And that makes sense because the energy needed to break down the mineral, sulfite or any other ones, it is quite intense. However, when you add organics, if I would go back to oops, this one, the pathway. You see here those different layers? Do you see now? there's biofilm surrounded with oxygen. My hand, I had an encounter with a chainsaw while chopping wood. So that wasn't very good. So you can see this ground, and then you see the next layer and the next layer, and then you see the erosion pit. That is where the microbes, that's the anode and that's the cathode. But on top of it, you have layers which consume the oxygen. And then when you change this oxygen layer by bringing in carbonate, the next biofilm is one which has no oxygen in it. It consumes the oxygen. So, you have a continuous cycle which is only altered. And you can see it also in the next slide. You see, this is the long-term storage that has, it's only here 5, and there is 10 micrometers. But you see, here's a totally different film. You don't have that equal pattern. That pattern is, basically because it dried out when we got it from the waste rock pile. It had dried out, not that we are putting it down. So, it's also the big difference in 1 million times. And obviously, you see, they eat the organics from the biofilm before. So they make one layer after another. Then you get that super, even kind of pattern. Next question. Have I answered it a little bit correct?
Yeah, thank you, Margaret. We have another question is, how do you think genomics can help the work that you are doing with microbes?
I think it's from my perspective, I don't only think. You see, I've never added any microbes. Look, it's very simple. The ones which know to live in this environment, how would you bring these microbes, even if you change them, how would you get them to the waste rock pile? The temperatures which are measured on the sun side of piles, I don't understand it. I tried to tell, I have a whole lecture which I presented to Ontario Genomics, and I also contacted the supercluster to assist with my information. But, academics, I guess I consider myself not such a let's say a high-nose academic, right? So I just have been working on these waste sites and read endless number of publications. So I don't think it's a pity. It's a pity that they don't. I would love to work with them so that it at least would give a little bit of success. However, it would be heaven if somebody would come or we would get the money to go to the site where all these things are now for 20, 30 years, depending, a million cubic meter lake, which is working. So we could go, I've fertilized the sediments and so on. We could go there with all this money, and then gene jogging, I call it. And, they could sample there and it would be the super demonstration site. I tried to get universities interested. These professors know everything. I'll tell you a good joke. This was no joke. I was working down in Salt Lake City, what was Kitimat? Oh, no. Yeah, I think so. Or the Bay, the Bingham Tunnel open pit, and they had a problem. They had sort of steps on the slides of the waste rock pile, and they had acid mine drainage from aluminum. Highly fascinated. So there was a professor at U of T who was a specialist in aluminum. So I had all these analysis of aluminum, and I couldn't make head or tails out of not the needed head or tails. So I thought, okay, I asked this professor to look at this water. So I brought him over the things, and $800 later, you know what he told me? Such a solution doesn't exist. I said, thank you very much. I mean, why don't I hear any laughter? Hello.
Yeah, yeah. We have another interesting question as well. There is it's talking about the altitude. This is specifically for the high Andes, the mountains where there are.
Oh, I worked in Baffin Island.
So the question is, will there be limitations to use this biotechnology in mines located above 3,500 meters over sea level? So in the mountains, like in the high Andes, if there is limitation.
Oh, you mean deep sea mining?
No. Over the sea level, the altitude in the mountains that are very high, more than 3,500 meters over sea level. So in these mountains, is there any limitation that the biotechnology that you are working could be used?
Oh, yeah. I mean, there are, I happen to be in my young years skiing, and there's algae there, and in Switzerland, and there are 4,000-meter high mountains. No problem whatsoever. There's, when you, depending on where you are, but when you go with the skis over the snow, you have some sort of reddish, pinkish stain. That's all algae or bacteria. So there's no problem. Microbes are everywhere. And the indigenous ones also. There's no, the highest I worked on Baffin Island on Nanisivik, we had minus 40 is there, and we had to stay there for a week. And so we excursioned around these slates, and it was amazing. There was warm water coming out of all the boreholes, of the exploration boreholes, and algae were growing there. They were frozen, but they were nicely green. So I don't think there's any problem. Okay. But I can, and the literature has so much of the information that the growth rates will be a bit slower, but they are protected in the wastes. But I don't see that there would be a problem.
Okay, thank you. I was wondering, in terms of the climate change and the different extreme events or increase on the temperature or the increase of the precipitation, but basically the change or the potential change in temperature, are there potential impacts in this biotechnology?
No. Warmer temperatures makes them grow faster. The other thing is, you see the extreme environments. In my time, I can't tell you when, in the middle of it, when I realized who is working with what. The Japanese, they were virtually doing research in every extreme environment, and I could, the one Yellowstone is only one, but I think most people know where Yellowstone is. But there are a lot of other very alkaline and highly acidic. I have slides of this too. Oh, I could, I could give talks on. I don't think there's. It's a. I would say for mining and for the contamination, it is positive, but only if you follow some of the ecological patterns. So the climate change, and one of the key things is that with climate change, we have more mining wastes. We have, toxic, lithium is highly toxic. And, we have wastes there. And most of the research, toxicology is, excuse me, some of the toxicology of the elements which are on Earth are radioactive. I mean, I've worked with rays in sediments from glaciers, and there are a lot of rare earths in, anyone interested, I can give I can discuss my report with it, the report to the hydropower plant. There are masses of rays in there. So, I had Bryn Harris, who is a metallurgist, evaluate the value, and then we submitted our report. And, well, there's probably 8 million, I don't have the number in my head. After all, it's getting towards the end of the day. But anyways, it's given free because the hydropower said, oh, the sediments don't belong to us, but we only rent the water. But I think that's the biggest concern I have. And if you go in my book and look at what Mike Sudbury had estimated, I pestered him with saying, Mike, how much water is used for mining? Blah, blah, blah. And he said, oh, it's not very much. Yeah, it's not very much in comparison to, it always depends what's much in comparison and so on. So finally he did it. And it does not look good. It's, it's just the agriculture is using so much, and we won't have any solution for, if we have so many people on the planet, how, and we are taking up with mining wastes, agricultural land, what is definitely occurring in China. So, the whole thing is so complex, and, what I really would love to do is get some interested, genuinely interested. I've spent my last money to give the stupid names to the microbes, excuse me, stupid names as well, my last 10,000 bucks. And so, maybe in June, I will know I was nominated to a World Sustainable Award, but that comes with a bit of money. And so maybe then I find some interested people come with me to South Bay, and then we could sample, and then we would know if the stuff works. But I have lots of field stuff, but already 30 minutes was good. Hopefully I made a reasonable job of explaining what I wanted to say.
Thank you.
So, more question?
Thank you, Margaret. We don't have another question at the moment. I don't know if there is another participant that will send a question, or if you want to open those who are attending now the microphone, you can ask as well. Yeah, I don't see other question at the moment. But yeah, I think we are as well close to the time, and I will like if there's no more questions now, I would like to, from the Environmental and Social Responsibility Society, I would like to thank you, Margaret, for your presentation. This presentation as well is recorded, so we are going to share that through our website and as well on the LinkedIn. So we're going to share the link that you can review again. And I share as well your book, a link on the chat, so those who are interested as well, they could.
Yeah, there is an internet like there's a book which you can really hand and read, or there's also paperback versions Springer gives, and also purely electronic, right?
Perfect.
So
Okay.
you know, anyone who, hopefully I didn't touch on any sensitive souls with my comments, but I think, you know, it doesn't go any different, because 40 years in this was a great time. But
Okay, wonderful. Thank you, Margaret, for your time, and thank you all for be here. And we're going to share soon the link as well for the all this session. Thank
yeah, and if you said you reviewed my book, let me have a look at it, and you know, we can use it for advertising. Oh, by the way, there's already 2,200 downloads. What they exactly mean, I don't know.
Okay.
But Springer is very impressed.